So we're going to take a look at our center of mass calculations here. And we're going to specifically look at number 49. Again. When smart boards go bad. All right. Now, we have an 18 by 18 meter raft, mass 6,800 kilograms, being used as a ferry boat. And then we have 3 cars, each of a mass of 1,200 kilograms on the northeast, southeast, and southwest corners. Northeast, southeast, and southwest corners. And so now they want to know what is the center of mass of our ferry boat. Well, I, as a problem solver, would probably choose either the center of mass of the ferry boat, which is what they did in the back, or my favorite alternative would be to place my origin right here, because that zeroes out one of my masses. Okay, so zeroing out one of your masses is a thing. And so if I do that, then I have a relatively, keep in mind this is 18 meters, and so that means the coordinates of the center of mass of my ferry boat are at -9, +9. The coordinates of this point are at 0, +18, and the coordinates of this point are at -18, 0. Does everybody see how I'm taking that origin and turning those into those coordinates? Yes, sir.
I think the mass of the boat itself doesn't matter.
The mass of the boat itself is going to matter, yes. The mass of the boat, why wouldn't it? It's an object in my system, right?
Yeah, but like...
If I were to choose the origin at the center of mass of the boat, then the mass of the boat would zero out in a calculation. And in that case, it technically would not matter. But it would matter when I do the total mass computation.
But like, if there's a boat, then like all the weights are going down all the same throughout the entire boat. So if you're adding mass on 3 corners, then we can, like, I feel like the boat itself won't affect the result.
It does, and I'll show you where it does when we do the computation here. Okay? So let's walk through now and do the center of mass relative to our origin, and that's the key. So we get the center of mass is 1,200 times -18, 0, plus 1,200 times 0, 18, plus 1,200 times 0, 0, that term's going to be invisible when I add it up, and plus 6,800 times -9, 9. So we're going to divide that now by the total mass, which is 3 times 1,200, or 3,600, plus 6,800. Now, coming back to your question, Stephen, if we had chosen the origin to be at the center of mass of the boat, then all of these numbers would be shifted by 9 in both directions, right? And in particular, the boat's numbers would now be 0. This would become invisible here, but not down here. Because the boat has mass, it is going to level out the effects of these cars right here, so that in the extreme case, if each car was just a fly, then the center of mass would be at the center of the boat, because the fly's mass would be swamped, overwhelmed by the boat's mass. In the other extreme case, if this ferry were just a thin shell with no mass to it, then my center of mass would be pulled down towards this guy, and the whole thing would go shunk and sink, capsize. Does that make sense? So the mass of the ferry matters in the denominator as well as in the numerator. Okay, so back to our original thing. We do some computations here. This is going to give me, oh, I don't know. kind of a pain to compute, right? 1200 times negative 18 plus 6800 times negative 9 divided by 10,400. And notice what I did there was to go through and do just the x's. I walked through and did x, 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 and divided. And now I'm going to walk through and do just the y's. Y, 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 and y. And if I'm really smart, then I would recognize that I should get the same numeric value as I did for the x's because of the symmetry of the situation. So this is the answer that I get, the center of mass. Then I look in the back and they say, no, the center of mass is at negative 1.04 comma positive 1.04 relative to the center of the boat. So the question I have to ask is this the same physical location? Well, that's easy enough to figure out. If my center of mass is right here at negative 7.96 comma positive 7.96, then I can change my reference frame, move my reference frame by simply adding 9 to this and subtracting 9 from that. And when I change my reference frame so that this point is now at 0, 0, adding 9 to this, I get 1.04, subtracting 9, I get negative 1.04, and that's it. I'm just doing a translation, like you guys learned how to do in trig, right? I'm doing a translation of the x's, and since I'm moving my x coordinate back by 9, I'm going to add 9 to my coordinate. Since I'm moving my y coordinate up by 9, I'm going to subtract 9 from that coordinate. Alternatively, when I look in the back and see that I get this answer relative to the center of the boat, I could just go back and recompute using 0, 0 as the center of the boat. Does that make sense? Yeah.
I think, could you, if you wanted to like avoid like using negatives in your answer, could you like essentially like rotate the code?
Sure, absolutely. Yeah.
So that would,
You could simply take this direction to be positive.
that's it.
Yeah.
But like, what I did is I like rotated the code. Like, so
Yeah,
it's like
yeah.
this.
Yeah, but then you have to keep track of which way is south.
I did.
Yeah. Amy, does that help with your question?
Yes.
Okay, good. Then, have any other questions before I move on to the main thing? Go.
Can we do
35.
Is okay, go get a pencil sharpener.
A collision, fantastic.
Yeah.
What'd you do with number 35?
Is that there? Or is that?
Pictures of your,
Then it's,
that thing, what is it? States. States, that's right, initial and final states. What does your initial state look like?
we initially have we have the car that's got 920 kilograms,
Mhm.
and it's going,
It is a sports car, it must be red.
No, it was like yellow. It has to be yellow.
and then I had it going to the right with a velocity that we don't have.
Okay.
And then there's an SUV,
Which must be black.
Why does it have to be black?
It apparently is a Kia. It's a shade joke. Kia is a boxy cars.
Okay,
They do.
it's 2,300 kilograms,
Mhm.
and its velocity is 0.
So,
And then for the final states,
Uh-huh.
the sports car runs into the SUV, and everything kind of blocks
Yeah.
that are together and they go forward 2.8 meters.
What type of collision is this?
Inelastic.
Good. Very good. Okay. They lock together. Now, hopefully, for your final state, you had something like this. Because the sliding of 2.8 meters is something that happens after the final state occurs. So in our collision, the collision process examines right before the collision, right after the collision. And then, as they slide 2.8 meters, during the sliding process, external forces are not negligible. And we know that because we know that they come to a stop. So something has to be changing their motion. And what F word is changing their motion? Absolutely. So that's an external force that's not negligible. It is only during the collision that we can ignore the external forces. So we can break this really up into two parts. First, our collision, and then a standard sliding kind of a problem that we've been doing since like chapter 2.
So, like in this picture, the finals really the initial.
Now the police officer knows that the coefficient of kinetic friction between tires and road is 0.8.
Whoa.
Interesting word that's used there, kinetic friction. Does that surprise you?
Yes.
Why? What do you know about tires rolling?
So that when tires roll, not the entire bottom of the tire touching the ground, it's just one point
Yeah.
at a time. So
That's right,
it'd be
and that
static
point is
friction.
pushing off the ground, so it has static friction. If my tires are experiencing kinetic friction, it means they're doing what?
They're not rolling.
Sliding,
They're
that's
sliding.
exactly right. Is that appropriate in this case? Yes, exactly what happens. Wheels lock up, you start sliding into this. I taught a student a long time ago, who's now in college, and she, her father is a state trooper, and he and I got into a discussion, 'cause she was in my physics class in the Navy physics, and we got into a discussion about how police officers come back and analyze crash scenes to determine how fast people were going. And they do exactly this. They have a big table of different models of tires versus the road versus the conditions. And they look up in the table, okay, you've got Goodyear blah 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 tires and it was dry, and so therefore the coefficient of kinetic friction was blah blah blah. And so now based on the skid marks, just the length of the skid marks, they can tell how fast this whole thing was going at that time. And based on how fast it was going after the collision, they can work backwards to how fast we were going before the collision.
Do they like?
You told me you were only going 30 miles an hour. Physics determined that was a lie. I'm ticketing you for 75. Yeah.
Do they actually like use this kind of calculation?
Yes, precisely these calculations. This is
That's
real life forensic stuff right here.
That's
All right. So, now what? Can we make some forward progress, or can we work backwards to get anywhere? Don't stall out. You don't need to have the entire problem solved in your head before you start. All you need to do is to make some forward progress based on your initial and final states. Can you do that? Go.
So the more inelastic we let go, the vehicle is
Yeah, in fact, that's true for every collision. So, yeah. So go with that thought. What do you get? Go ahead and tell us. And we
Okay,
can,
so, yeah,
you already told me that.
yes. And I just kind of wrote that down in terms of mass and velocity. So I just did,
Go ahead and give me the numbers.
okay, so 920 times 3
Uh-huh. You would, but,
Oh,
yeah, but it's invisible.
and then you do 920 plus 2,300, which is 3. Times
Yes. Notice that you talked us through that, which was fine, but we can actually write that equation in a matter of about 15 seconds. 920, just by looking at our state diagram, we can say 920 times V, momentum here, has to equal, well, we have to do the addition, 3220 times V final. What does this tell us? This tells us an important thing, and that is that the V final is going to be proportional to the initial velocity, and that proportionality constant is going to be 920 over 3220 equals 0.286. Okay, we have made forward progress. We have related the final velocity of our system to the initial velocity of our system. Okay, clearly we're going to have one additional equation in order to get enough information to find either V or V final. So that information is going to have to come from the skid marks. What can we say about the skid marks? How do I draw the situation that's occurring as our car is skidding, as our cars are skidding? Draw them as one object, yep. So definitely, I'm just going to draw them as one big blob.
Yeah, here, coaster.
Yeah, that's right. One big blob.
The kinetic energy for when the kinetic energy from whatever it was to 0 during this game on.
Yeah. The kinetic energy is going to change from whatever it was to 0. What causes that change?
Friction.
Which does
Work.
work. That's it. So we can set the work done to friction equal to the change in the kinetic energy. And we know that the final state is 0, and the initial state is 1/2 of m v final squared. And also, work done by friction. We'll need to know the force of friction. That calls for a free body diagram. mg, Fn, and frictional force pushing backwards.
V.
What's that?
V.
Do you have to include a free body diagram?
Okay.
Well, it's kind of like this. At this point, you guys are fairly expert, and most of you can recognize that the free body diagram for this situation is going to be that, right? So in very common situations, if you kind of gloss the free body diagram and give me the right equation for friction, I'm not going to complain too much. However, if there's the least sign of trouble, I'm going to ask you, where's your free body diagram? So I would say, be smart about this. I'm going to give you a little bit of leeway because you guys are good, but so therefore the work done by friction is going to be equal to negative F times the distance traveled, which is the same as negative mu mg times the distance traveled. And I believe that we have all of the numbers we need. Notice that the mass is 3220, so the mass cancels out. Once these guys start skidding, it doesn't matter how much they weigh. Also, the negative signs cancel out.
Is that mu?
Mu. Because the force of friction is mu times the normal. And the normal force in this case is the same as g.
It feels like forever.
Yeah, yeah.
Wait, what's D?
And d is the distance that's traveled. Remember that work is equal to force times distance times cosine of the angle between.
Sorry, I didn't.
We'll come back to that because there's another way that we could have thought about this. Right? And so we get mu, which is 0.8, times g, which is 10 meters per second squared, times the distance, I believe, is 2.8 meters. Is that right? And solve for V final, and once we have V final, we can now take that back to our original relationship in green and solve for V.
Wait, can you scroll down for a second?
This is a great problem. I can totally imagine this showing up on
Wouldn't
a
it be
test.
negative 1/2?
No, the negative sign's canceled out, and the reason for that is we are losing kinetic energy. And the reason we're losing kinetic energy is that our cars are experiencing a force opposite the direction of motion, so that that force does negative work on them. Now, Mac, you mentioned that you did this in a slightly different way. I'm going to leave the rest of the details up to you, Amy, and any of the rest of you that need to. Mac, how did you proceed?
Okay, well, I set up my velocities as velocity for the sports car
Okay.
and the velocity of the SUV. So, and then like in V3, which is the velocity will be like
Right.
skate.
Same variables, different labels.
Yeah.
Okay.
So I used the conservation of momentum.
Yep.
And then I found friction.
So you got everything that we got in green.
Sort of.
How'd you know 6.63 meters per second? Oh, you worked backwards. You got to this point and then went off. Didn't you?
Yes.
Okay. Yep. Okay. So talk to us about the analysis that you did once you were ready to analyze the skid.
Okay, well, so I figured that since the two products from the crash are down as a friction,
Yeah.
there has to be an acceleration.
Aha. So he considers acceleration rather than work. Perfectly legitimate fundamental quantity to use. Okay?
So, to find that, you would have to use like force equals ma.
Ah.
I just needed to find force,
You just needed to find the
which
force,
is friction.
which was the frictional force.
So I used friction equals mu sub k times that.
And was equal to mg. And you set that equal to mass times acceleration. Hopefully there's a negative sign in here somewhere, right? Because the friction is pointing.
Right.
Yep.
And then, well, you plug that in, you would eventually find acceleration.
Which is negative 8 meters per second squared.
Yeah. I'm using my own
Yep.
Okay, and then, I used a kinematic equation.
And then you used equations of motion. Exactly right. So, and we had the acceleration. And we had the distance. And we had V0 was our V final from before. And we have the final velocity is 0. And so we get solve for V final. And you get exactly the same V final that we got in the previous one. And you work backwards to solve for V. Good. Very good. What these represent are the two different possible approaches that physicists could use. The first approach, which I'm going to call the energy approach, takes a look only at initial and final states. In this case, the initial state is right after the collision. The final state is once everybody has stopped sliding. And considers the change in energy. And to do that, consider the change in energy, you need to consider how much work is done during that process. The second approach is to find the acceleration in general as a function of time, but here we got lucky, our acceleration was constant. And because it is constant, therefore I can use the equations of motion with constant acceleration. and then I can solve for V final. These two approaches always give the same answer because they're really the same thing in disguise. But their computations are so different from each other that we could almost treat them as two different ways of doing the problem. If you were to take this equation right here, right there, multiply both sides by 1/2 m, what you would get is 1/2 mv squared, kinetic energy final, equals 1/2 mv0 squared, kinetic energy initial, plus m times a times delta x, or f times delta x, or work done. So they are actually the same equation, but the approach to it is so different conceptually that we almost think about it as two different things. When we do AP Physics, what we basically do is to learn how to do this first, and then how to do the energy approach. And different circumstances lend themselves to easier here or easier there. Yes?
How did to understand like the top part, but how did you get from the v squared equals v initial squared, and you got the 0 equals v final squared?
Oh, okay. So what's happening is, if we look at our thing here, we had a V and we had a V final after the collision, right? Right after the collision is when the sliding starts. And so from the perspective of analyzing just the collision, the 2.8 meters that we slide right here, the V0 is the velocity we have at the start of that slide,
Okay.
and the V final is the velocity we have at the end of that slide, which is necessarily 0.
Okay.
And so we use the V0 at the start of the slide as the V final from the end of the collision.
Okay.
So we're picturing two different processes that dovetail each other, and the end of one is the beginning of the next.
Okay.
Good. Better? Okay. Let me see how much I want to get through here, and let me see how much time I've got. I think I've got 10 minutes. Yep. Okay. Let me just make sure that I don't need to cover anything here.
Yes.
All right. Let me see how far I can get with this. What I want to convince you is that the reason that we care about computing center of mass is that we can treat a system of objects as essentially one object whose mass is all concentrated at the center. Any system can be treated as a single object with the total mass concentrated at the center of the mass. Now let me show you what I mean by this. First of all, has it ever bothered you that as we've been doing all of our equations, we've been treating objects, say Mac, as one object instead of the trillions of atoms that make up his body? Is that bothering you? You know what I'm talking about? No, you don't know what I'm talking about. Well, think about it like this. So, imagine for a moment that Mac's superhero power involves getting into fights or something like that. And, so he's squaring off against Physics Man and takes a It's a salad, whatever.
Super triangle.
That's right. And so we would say F equals ma, right? And so we would compute the acceleration of Mach. But if you stop and think about it for just a second, Mach's body is not one object, really. It really consists of trillions of atoms that are all bonded to each other in various ways. And technically, when I apply the force there, what I'm really doing is applying just to these atoms right here on the surface. And then they, like, push other atoms, et cetera, and the result is that he doesn't go, like, rigidly straight back, but he actually kind of, like, flops or something. Right? So, something like that, right? So the question is, given that his body actually consists of trillions and trillions of atoms, what justifies me treating him as a single object? And the answer is that as long as I concentrate all of his mass at the center of mass, which is located right out there, then the math still works. Have a seat and let me show you why. Yeah,
Here is center of mass of human body.
yeah, more or less. The legs weigh a whole lot.
So wouldn't that be lower? Over.
Well, I pointed to about right here. Could be, a little bit up, a little bit down. Kind of depends upon how the mass is distributed. Max pretty close, I think. All right. So, one. Yes.
I think you've got confidence. I think you're still Yeah.
All right. So why?
Okay.
Let's go to our computation x center of mass right here. And let's consider what the x center of mass is. And the x center of mass is the weighted average of positions. It is the sum of mass times position divided by the total mass. Now, the first thing that I want you to see is that if I simply multiply both sides by the total mass, what I get is the moment of a single object whose location is the center of mass and whose mass is the total mass. And that is equal to the sum of all of the moments, that's mass times position, of all the objects added together. That's the first thing.
Can you say that?
Yep. The moment of my single object is the total mass times the position of the center of mass, which is equal to the sums of all the individual moments of all the constituent parts. That's the first thing. Now let's look at rates of change. The rate of change of each of these is going to be the velocities, right? So when I take the rates of change here, calculus people think derivative, then what I get is that the mass times the velocity of the center of mass is the sum of masses times the velocities of each of the components. But wait, this is the total momentum of the object, mass times velocity. And this is the sum of all of the individual momenta of the constituent parts. I didn't insert the V. I said, let's take a look at rates of change.
Oh, okay.
As X changes here over time, as each constituent part changes over time, the rate of change of the position is the velocity. Yep.
So the fact that it's velocity of the center of mass and not just velocity doesn't change?
Nope. Specifically,
You take the center of mass as the entire object.
yes. So what I'm getting is that the momentum of my system, taken as a whole object, is simply the sums of all the momenta of the constituent parts. Okay. Now here's where this gets applied. Let me show you how cool this is. Romeo and Juliet are sitting in a boat.
This doesn't look good. Already.
Standing on a boat.
Aren't they so far apart? Huh? Yeah.
One hair.
With the wool
Romeo Romeo, being a boy, thinks it would be romantic to throw a bowling ball towards Juliet. Why?
Kids these days.
That's
You'd
right.
be surprised.
The question is, what happens to the boat?
She's gonna fall in the water.
Now, this is really interesting. Watch what happens. Before the throw, the total momentum of my system is 0. Romeo's sitting there, Juliet is sitting there, the boat's sitting there, and so is the ball. So nobody has any momentum. While the ball is in midair, the ball is carrying momentum in this direction. But there are no external forces, so the center of mass of my system cannot move. And if the center of mass cannot move and the ball is carrying mass this way, what does everything else have to do? It has to go to the left. Exactly it. It has to go to the left. So when he throws the ball pushes on him, and as a result, he and the boat with it all go to the left. She catches the ball and throws him a dirty look. When she catches the ball, what happens to the boat? It stops. How do I know? She catches the ball, she brings the ball to a stop, the momentum of the ball is now 0, the total momentum never changes, it was 0 to begin with, it must be 0 afterwards. So that during this entire process, the total momentum of my whole system never changes from 0, because there are no external forces acting on it. We're going to do a little more system.
Here's the,
Sound like a Bravo.